Say a gorilla is sleeping and a chimpanzee is standing on a very thin ice in the middle of some ocean. Now, because the ice is pretty thin, their weights can break the ice, right? It's possible because of their weights. And so the question we want to try and answer in this video is figure out whose weight is more likely to break this ice. Is it the chimpanzees or the gorillas? Now, before we come to any conclusion, let's first look at some data. Let's say the chimpanzee weighs about 30 kilogram, and let's say the gorilla weighs a staggering 150 kilogram. And imagine that because the chimpanzee is standing, the area of contact with that ice is pretty small. Let's say that area is about 100 centimeters square. That's basically the area of his feet. And because this gorilla is sleeping on his side and gorilla is large, that area of contact is going to be pretty big. Let's say that area is about a meter square. And remember, a meter is 100 centimeters, so this area is much bigger than this one. Okay, so whose weight is more likely to break that ice? Now, at first we might think, hey, gorilla definitely weighs so much more than the chimp, so it's definitely his weight could break that ice, right? But remember, whether you can break something or not just depends upon your force, but it also depends upon how concentrated that force is. For example, if you were to push on a paper with your thumb, there's a good chance you won't break that, you won't pierce through that paper, right? On the other hand, if you were to put that same force on that same paper, but now you were to push it through a pin, I'm pretty sure you can easily puncture that paper, right? Pierce through that paper. Why? It's not because you put more force, but because over here, notice the force was divided over a large area. But here the force was concentrated into a tiny area. So what also matters is not just the force, but what also matters is the area of contact. And so, in other words, what matters is the pressure. It's the pressure which tells us how concentrated the force is. It's the pressure that tells us whether something is going to break or not. More pressure, more chances of breaking it. And how do we calculate pressure? We calculate pressure as force divided by area. That's what it is. How much force is getting divided by the area, right? And we've talked a lot about this in a previous video called thrust and pressure. And so if you need more clarity on, where this formula comes from, great idea to go back and watch that video. Anyways, in our example, which force are we talking about? Hey, it's the force due to their weight, isn't it? That's the one that is pressing on that thin ice, which could break that ice, isn't it? So this force in our example is going to be their weights. And so in our example, we will calculate that pressure as their weight divided by the area. And how do we calculate their weight? Weight is not the same thing as mass. Weight is a force due to gravity, right? And how do we calculate force? Well, if you use Newton's second law, force equals mass times acceleration. And since we are dealing with gravity, that acceleration will be g. And so we'll calculate weight as mass times g. And therefore, in our example, the pressure will be mg divided by the area. And again, we have spoken a lot about why weight equals mg in previous videos called mass and weight. And so again, if you need more clarity over there, you can feel free to go back and check that. And so now that we know how to calculate pressure, can you try and calculate who's putting more pressure on the ice first? Good, give it a shot. And just to make the calculation simple, let's assume g to be 10 meter per second square instead of 9.8. Okay, so pause the video and give this a shot first. All right, so let's first do pressure due to the gorilla on the ice, g for gorilla. It's going to be the mass of that gorilla, that is 150 kilograms, times g, which we are assuming to be 10 meters per second square, divided by the area of contact. The area of contact over here is 1 meter squared. Okay, what's that going to be? Well, let's write that down here. That's going to be 1,500 kilogram meters per second square, but kilogram meters per second square is the unit of force, the unit of weight, and that is also called newtons. right? Divided by 1, which is 1,500, and we have meter square in the denominator. And so that's the pressure due to the gorilla. It's 1,500 newtons per meter square, which we can also call pascals or pascals. So 1,500 pascal. That's the pressure due to gorilla. Okay, now let's do the pressure due to the chimpanzee. And if you had not tried this before, again, now would be a great time to pause and try it. A small thing over here is, the area is in centimeter square. So we need to be a little bit careful before we compare. Okay, let's do it. So the pressure due to the chimpanzee on the ice, let's call it as PC, C for chimpanzee. It's going to be the mass of the chimpanzee, which is a very tiny number. It's just 30 kilogram compared to the gorilla, times 10 meters per second squared, divided by the area, and that area is 100 centimeters squared. So let's divide this. The zeros cancel out, and I end up with 3. I get 3 kilogram meter per second square is again Newton, because that's the unit of force, divided by centimeter square. And at first we might say, hey, look at this. This is such a small number compared to this. This is 1,500 and this is just 3, right? But we cannot compare directly because the units are not same. This is in meter square. So let's make the units same. So let's convert this centimeter to meters. How do we do that? Well, we know 1 meter is 100 centimeters. But since I want to convert centimeters to meter, I want to know 1 centimeter equals how many meters, right? So in this equation, I'm just going to divide by 100. So that right-hand side, I'll have just 1 centimeter. And so if the zeros cancel, we get 1 centimeter is equal to 1 over 100 meter. And so all we have to do now is just do the calculation and see which number turns out to be big. So let's see, we get 3 newtons divided by, a centimeter is 1 over 100. Let me keep that as fraction itself. Let's go down a little bit. Okay, so 1 over 100 meter squared. That's what a centimeter is. So let's carefully solve this, simplify this. 1 over 100 meter square becomes, well, I'll get a meter square over here in the numerator over here, divided by 100 square is 1 and 4 zeros, so 10,000. What is that equal to? Well, whenever I have a fraction in the denominator, let's be very careful, I like to write this as the product of reciprocal. So I can write as 3 newtons into reciprocal of this, so 10,000 divided by meter square. And that gives me, look at that number, 30,000. 30,000 newtons per meter square. Ooh, that's a big number compared to the gorillas. So that is, Newton per meter square is pascals. So 30,000 pascals. That is the pressure. So let's put everything in one frame so we can see everything together. Okay, so what we see is that the pressure due to the chimpanzee is super high compared to that of gorilla. I mean, look at that. Why? Why is chimpanzee weighing so low, putting so much pressure? That's because he's standing. And so all his weight is being concentrated into a tiny area. And that's why it's putting an enormous pressure on the ice. So you see, because chimpanzee is putting a larger pressure, this means there's a bigger chance that the ice can break due to the chimp, not due to the gorilla. Of course, I'm assuming that the ice is pretty much uniform over here and here, okay? But anyways, this tells us something, right? I mean, if you ever find yourself stuck on some thin ice or something like that, which is better, to stand on it or to sleep on it? Well, to sleep on it, right? Because when you sleep on it, your pressure decreases.